it's 100% natural.
Yeah.
So we should be live at this point. Hello, everyone. Right now we're getting ready for the presentation of MESS, the Modified Exponential Subjective Scoring, that is going to hopefully help stop a lot and really crank up hash rate in ETC. It's good to be back. I missed you guys. I was very lucky to be part of the team again now, with developer relations being my role. So I'm excited to be part of all of this. And now we're taking a look at MESSnet TV. What's happening now on MESSnet?
So we have just kicked off a sample attack. So the screen that you see in front of you is a part of our test running orchestrator. Just to give a quick overview of all the pieces here and what you see. At the top of the screen, you see a network of interconnected nodes. And actually, for those in the audience, if you want a slightly less pixelated version of this, you can go to mess.canhas.net and load it on your own screen.
That's the link in the chat, guys. Mess.canhas.net, so you can see our live simulation of attacks on MESSnet.
So at the top of the screen, you can see all of the interconnected nodes in MESSnet. We have, let me pull up the specifics. We have 149 servers spread across 39 different data centers operated by 2 different cloud service providers on 5 different continents, making up our MESSnet that we put together to test the modified exponential subjective scoring. And so at the top of the screen, you see all of the interconnected nodes. So these are standard Ethereum nodes, connect to each other via the peer-to-peer systems. And as one of them discovers a block, it propagates through the network. And so the colors at the top of the screen reflect reflect the latest block that each node has seen. And we're seeing a lot more colors that I'm used to. I'm not sure exactly what's going on, if it's just latency, or I guess it's stabilized.
We have plenty of time to figure it out, guys. Everybody just entering. We're spending the first few minutes to give people time to come in. We're going to re-talk about everything. Don't worry, you haven't missed anything. We're making sure that there's plenty of time for people to be part of the chat before we kick it off. But at the same time, we're enjoying the view.
So down at the bottom of the screen, you see the history of each of the nodes at the top of the screen. So each column in that table, of that colorful table down at the bottom, represents one node in our MESSnet network. The color of each row represents a block number, and the color represents which block that node had at that level. So we have a bunch of different miners who are all finding different blocks. When they find a block and it propagates through the network, you see that up at the top in the nodes all changing color, and you see it at the bottom by the entry of a new row. It does look like we have a handful of nodes that might not be online at the moment. So you see the empty columns down at the bottom. And then...
Yeah. Also, I think worth mentioning that the way that we're watching this is, so what we see is limited by basically our TV reception. And so if we have a lot of people on this website, this is something that we pulled together just for this and to give us a view. So it's not, I know that there's, with the thousands of people logged on watching MESSnet right now, might introduce some lagginess too. So if it looks like blocks aren't getting imported by a node, or they're not reporting their head, that may be the case, but it also may be the case that our WebSockets are just bogged down.
So about down at the bottom, about a quarter of the way across the screen, from the left of the screen, you see one node that's starting to creep out ahead of the others. That is our attacker. So that node is offline. It's disconnected from the rest of the node. You can see them in the upper left-hand corner of the network. That it is not connected to anybody. It's just sitting there mining nodes on its own. And we've turned the hashing power way up on this node so that it can mine more blocks. Now, what we expect to happen here, if we've tuned everything correctly, is that node should mine more blocks than the rest of the network before the test is over. But when it reconnects to the rest of the network and dumps those blocks on the network, as a 51% attacker might do, the network will reject those nodes. So it's going to run for about 20 minutes. And based on the modified exponential subjective scoring, which I think Isaac's going to explain in a few minutes, the rest of the nodes are going to say that it has not achieved a difficulty level high enough to overcome the blocks that it's on. So even though it will be the longer chain and the heavier chain, it will be rejected because the rest of the nodes will identify it as a 51% attack.
Okay, so I think this is we've got a good amount of people here. I think it's good time to start going over the agenda. So today I'm Dean Pappas, Developer Relations at ETC Labs. We also have with us today Isaac Artis, who's the head developer at ETC Core. And we also have Austin Roberts, who's the CEO of OpenRelay. Welcome, guys. Thank you for taking the time to do this presentation of MESS.
Yeah, thanks for having us.
So I want to kind of go over, why MESS, what MESS, what we're doing, what we're trying to achieve with this proposal, and what we're trying to achieve with this presentation. This is all because of the low hash rate that Ethereum Classic has had recently. So this proposal to develop a finality algorithm is called MESS, and the idea is that it will help raise chain state finality near exponentially, which basically means it'll make it more expensive for somebody to attack. There's a few articles we'll share later after the presentation that discuss how much more expensive those attacks would be, making them virtually impossible. During this presentation, we're going to discuss artificial finality as a concept, go over some of the ideas that the team discussed and reviewed before coming to the conclusion that MESS was the best way forward. Then we'll have a quick explanation of this. And during this time, we have a live demo of MESSNet. Now, what MESSNet is it's a simulation of an actual 51% attack happening. There's a lot of different versions and types of simulations we can go through. I think, correct me if I'm wrong, Austin, this is a 20-minute simulation. And in this one, we have an attacker coming in and then getting rejected by the nodes.
That's the idea, yes. Essentially, this attacker is going to disconnect from the network, mine for 20 minutes at a about 1.2 times the hash power of the rest of the network. So they should be produce about 20% more blocks in the same period of time as the rest of the network. Yet over a 20-minute period, that 20% will not be sufficient to. Sorry. This one's 10%. That 10% will not be sufficient to overpower the network.
So I can tell there's a lot of variables you have to use to choose when you're putting the simulation together.
Right, and yeah. So the key variables that we look at are how much more hashing power do we want the hacker to have versus the rest of the network, and then how long is it going to run? So if the attacker is going to run for 10 or 20 minutes and we expect them to succeed, then they've got to have, say, at least 1.2 times the hashing power of the rest of the network. Whereas normally, 1.02 ought to be sufficient for an attacker to succeed at a 51% attack.
Excellent. So, Isaac, do you want to run us through an overview of artificial finality?
Sure. So I'm going to change my screen here so I can have some different visuals. And right here, what I'm looking at is the ECIP that we have proposed. It's actually an ECBP, which stands for Ethereum Classic Best Practice. And I just updated this yesterday. So if you looked at it last week and haven't since last night, please feel welcome to take another look at it. This is the best graph that I've made about this so far, if I do say so. When we're talking about this finality, artificial finality curve that we also talk about as anti-gravity, that's what this line is here. And this is the imposition that nodes running with the MES feature will impose on competing chain segments, and those are competing chain segments with they're competing with the view that the node already has of some state of the network. And so normally without MES, nodes will accept any block and any segment as long as the canonical head, as long as the difficulty is greater. But we apply this curve to that difficulty comparison. So instead of a simple, is it greater than, we say, is it greater than this much? And that artificial sort of inflation or imposition causes the nodes to prefer to stick with the chain segment that they have instead of a new chain segment that would come later.
And it's worth noting that, for small reorganizations of, 2-3 blocks where, different nodes on the network, legitimately had not seen the other network or other nodes, the impact of this curve is very, very small, to the point of being negligible. So if you had two different chain segments that were maybe 3 blocks long from where they had forked from each other, a fourth block is just going to all of them over to that new or to that one chain segment. You've really got to be looking at a fairly significant number of blocks before this curve becomes significant.
Yeah, exactly. Yeah, we don't want to mess with, so to speak, the normal reorganizations that are a part of the natural life cycle of the chain, and those are the small ones. So that's this part of the curve, and this part of the curve falls well below the normal difficulty variance that even very near equivalent difficulty chains will have. So it really only comes into effect for this part, which is the suspicious part. Man, I wish I could see you all and just ask you to blurt out your questions. If you do have any questions, I'll keep an eye on this chat here and would love to field them as they occur.
Please use the ask a question area in case we miss anything. And of course, we're always available in the Discords, both the ETC Core Discord and the ETC Community Discord. We want questions right now. It's important that everybody understands exactly what MES does.
Yeah.
So when we're talking about artificial finality, there's really kind of a balance of several different concerns. With the 51% attacks that Ethereum Classic has seen over the last couple of months, it has been, obviously our primary goal was make it so that somebody can't, reorg out, 12 hours worth of transactions and make it so that they never happened. So we're trying to reduce the probability of 51 or increase the cost of executing 51% attacks is really what it comes down to. Or at that point, they're not really 51% attacks, but of double spend attacks. So the other concerns that we need to address are, are we introducing an opportunity for somebody to split the chain? So, some of the early things that we had considered, and we're not going to go into too much detail on these, I don't think, things like a reorg cap, where a node just says, I'm not going to reorg anything older than 128 blocks. And if I see 128 block reorg, I'm just going to stay where I am and reject that block as invalid. And that's actually what Open Ethereum did during the first of the 51% attacks. It just flat out rejected anything older than 128 blocks and stayed where it was. Now, its reason for doing that is kind of a technical implementation detail, that it actually didn't have the information it needed in order to reorg, rather than then it made that as an active decision. But those nodes ultimately got stuck on the other side of the chain and could not reorg. And we don't want to create a scenario where an attacker can say, okay, we know there's 128 block reorg cap. So if I dump my 129 block chain on the network right as people are getting that 128th block, they could split the network. With the MES solution to artificial finality, we're able to, there is no hard line beyond which a chain split can't be resolved. Isaac has done some considerable work on trying to create such a scenario, and the best he's been able to do is if you have two attackers on both sides of the chain, both refusing to switch to the other side of the chain, not because they're not following the standard rules of a standard client, then you can kind of force other people to align with one of those two nodes. But you have to maintain that. As soon as one of those attackers goes offline, or both of those attackers go offline, the network will resolve back to a single chain. So the only way that somebody could execute, unlike with a reorg cap where somebody could potentially split the network and the network could never resolve itself, with MES, if somebody wants to split the network, they have to maintain that split indefinitely, which is a very expensive proposition.
Yeah, when I wrote the digest, we were saying that it was around like 70 times more, or 35.
70 times more was with an earlier version of the parameters for MES. Ultimately, that ended up around 31 times.
Oh, okay. Yeah. So to put the it's a huge. I mean, when you say that, maybe I'm profitable if I attack. When it's 30 times more expensive, it makes most of these attacks unprofitable.
Right. So I see in the questions, are there any downsides to MES? So the biggest issue really comes down to when new nodes are coming online. If there is a chain split going on, they don't know which side is the attacker's chain and which side is the honest side of the chain. They're not in the position to, if they don't have, if they weren't following the chain all along, they don't know which is the honest side, which is the bad side. So they're just going to sync up with one side of the chain, and they may end up syncing up with the wrong side of the chain. But really, the value to MES is that if the attacker doesn't sustain their attack indefinitely, which is an expensive proposition and they can't plausibly afford to do so, if they don't sustain their attack indefinitely, eventually the side of the network that rejected the attacker's chain is going to become the stronger side again. And anybody who missed out at the beginning is going to reorg back onto that.
And it's worth saying that Eclipse attack scenario, although MES can and would potentially exacerbate the impact of that for a victim, that scenario is one that exists right now and is a possibility right now. So the nice part about MES is that unlike some other artificial finality curves, basically, that scenario or state of destitution for the victim node is escapable and recoverable. And it will be escaped and recovered so long as the attacker maintains anything less than 1/31st of the honest network's hash power. And then there are also, to that, because it seems like that's a concern, at least one of the foremost concerns for people, I think, because Eclipse is a familiar term, because it's been around as long as proof of work chains have been around. The implementation at CoreDeath right now has a couple of features that will hopefully avoid that by not activating MES until you get totally synced, and not activating MES if you have fewer than the default minimum of peers that you need to sync comfortably in the first place. And then if the attacker ever stops feeding you blocks, then there's a head staleness check, so you don't get kind of temporarily stuck on a completely abandoned chain. And that staleness check right now is 390 seconds. With those features, MES is enabled or disabled, so that we can only apply this feature when it's practical and very reasonably safe to do so.
I might want to point us back to the MES TV.
Yeah.
Our attacker is attempting to dump the.
Oh, here he comes.
So down at the bottom, you can see our attacker. Well, yeah. So our attacker has moved back in with the rest of the network. Down at the bottom, you can see about a quarter of the way in from the left of the screen. They are sitting there with several more blocks than the rest of the network. They are now connected to the rest of the network and trying to provide those blocks to peers, but because they did not have sufficient, they did not overcome the artificial finality curve. Nobody is accepting their blocks, and everybody is just moving on, mining on top of the regular chain. And even though they have the longer chain, they have the chain with the higher total difficulty, their chain is not being adopted. Now, in a couple of minutes, our test runner is going to automatically start running the next test, which is just going to run for about 10 minutes. And in that test scenario, the attacker will have sufficient power that they will be able to dump their nodes, or overcome the finality curve and dump their nodes on the network. So, yeah, you can see this one working. You know, one of the really neat things about MES is there's a fairly simple formula for the difficulty curve, and that makes it very easy to calculate that in order for an attacker to succeed at a 51% attack, they need to be able to produce this much more hashing power than the entire rest of the network. And so, you know, the math on that has been fairly simple. And you know, our running MESnet, you know, once we worked out a couple of issues in the early implementation, running MESnet, we've been able to see it, you know, reflect that math very cleanly.
So in this simulation, what percent, like, how much hash rate of the network does this attacker have?
So let me check. So in this simulation, the attacker had 10% more hash power than the rest of the network. So that'd be roughly equivalent to having, like, what, 55% of the hashing power of the entire network.
Wow. And it was really cool how you could see that one node by itself, you know, saying, hey, this is the chain, but every other node was like, yeah, okay, next time, try again.
Yeah. Yeah, so now we'll see it kind of level off, and then we'll start the second one where our blue
So
guy is going to sync
that
back up.
node, I don't see him anymore trying to push these blocks. What happened? He just gives up? He backs off?
Yeah, he runs
Once
out of money.
the network overpowered him, he would have accepted the blocks from the rest of the network. Part of the reason we take this node offline and disconnect it from its peers while it generates its blocks is because we do have it set up as pretty much just a normal node, and there's no special rules about what blocks it will and won't accept. It works just like the rest, except that it mines offline for a little while.
Okay, so this is now the end of the 20-minute simulation, and we're getting ready for the 10-minute one where we're giving an attacker more hash rate. Is that correct?
We're giving the attacker less hash rate, actually, I think, right, Austin?
Oh,
So,
actually,
shorter
no,
attack.
on the next one, we are giving the attacker more hash rate. So it will be able to overcome the artificial finality curve.
Okay, yeah. Okay. I want to do quick. Yeah, maybe I can talk about some of my experiments with the bifurcation vulnerability, because I think that's the one, and the risk of bifurcation is that's the most significant risk to any artificial finality solution or proposition. Because if you can split the network, then if I were an attacker, that's what I would try to do first. And then mount any different other kinds of attacks that you want. Once you're able to pull it apart, then you have lower hash rate on one side or the other to attack in the first place. And getting the nodes to agree, or at least to work compatibly, using their subjective views of the network is the real trick to artificial finality, because you want them to agree to disagree. And so I ran tests that were trying to do that. Trying to pull the network apart, which is a different scenario than what we're seeing on MessNet right now, which is kind of your standard bread and butter 51% attack. And as Austin said, I'll try to keep this short because he already did talk about this a little bit, but it is really tricky to do. And even with an attacker who was able to, and so the case where you'll see a network bifurcation with mess is when and if the attacker is able to produce almost exactly difficulty equivalent chains and sustain that for a non-trivial amount of time. So the question is, can you produce difficulty equivalent chains? And then if you can, what are the other variables that you need to contend with to even get that to fly? So I had an attacker who was able to and was producing blocks in exact lockstep with the honest miner. So it was going like block, 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 which is quite contrived and controlled. Because of course, like in the honest network, even if you have a backlog of blocks, if you come to the network with 10 times the hash power of the honest guys and can store up a backlog of blocks and be able to try to do that, you still need to contend with network propagations at the time when you hear about the honest guys block and when you're able to broadcast your own block.
And I would say network propagation times are a big part of the reason we ran MessNet with nodes on 5 different continents.
Exactly. Yeah, exactly. And so even running a simulation with 40 or 60 nodes just on my computer, so with almost zero propagation time and lockstep block production, I could not create a bifurcation case. which yeah, put me to sleep that night. Because along with network propagation, there are other variables, a lot of other variables that an attacker would need to deal with to produce an exactly equivalent difficulty chain. So just the normal network hash rate variability. So as miners come and go, as their rigs tune up or tune down, the network hash rate, the honest network hash rate does go up and down. Even the dishonest network hash rate does that. So that's an important factor, network propagation. The other big one is the disproportionate mining entity hash power share. So in my scenario, I had one good guy miner and one bad guy miner, and they were in lockstep. On the real network, of course, mining power is distributed, and moreover, is distributed disproportionately. So a handful of miners have the majority of power, while the long tail of miners have smaller shares. And so not only does the attacker need to get his blocks to half of the network, but he also needs to divide up that hash power share between the nodes and between the miners, which is really tricky, would be really, really tricky. And then there are also existing subjective arbitration steps like a coin toss for when nodes do find segments with exactly equivalent total difficulty and number. So yeah, it's hard to do.
Yeah, if it's hard to do in simulations, that usually means it's virtually impossible to do in real life.
I hope so. Yeah. Yeah.
So there's a few questions. There was this one we just got from Julian. Have you explored to analyze block timestamping tempering as an attack vector?
Yeah. Yeah, so that's kind of what I was talking about with a miner who comes with a whole bunch of hash rate and stores up a backlog of blocks. In that case, he's able to sort of use whatever timestamp he wants, but he will never be able to produce blocks that appear to them, so they can never be more than 1 second apart, timestamped more than 1 second.
Less than 1 second apart.
Yeah, less than 1 second apart. And again, integers. So 1 is the minimum. So even if he has 10,000 blocks stored up and he's able to produce those in half an hour, it's going to take him, because the nodes will at least not reject, but will not import blocks that come from the future right away. And they have a future limit. And so he is only going to be able to work that so far ahead of the network in terms of his actual broadcasts and application of those and proposition of those blocks to the network. It's worth saying that if an attacker can produce a huge number of blocks, like with a huge amount of hash power, and is able to produce maybe 2,000 or 3,000 blocks that have 1 second difficulties, 1 second offsets, which is the maximum difficulty increase, they can beat the curve for as much hash power as they have. But what the miner is going to contend with as they bring all that hash power is that with every 1 second block that they produce, the difficulty does go up. So you have to be a huge, huge whale to beat the curve. And hopefully so much so that there is not that big of a whale in existence right now.
Yeah, and some of the simulations, my understanding is that you wouldn't even be able to purchase that much hash power. It doesn't exist on NiceHash, for example.
Yeah, we're looking not just at the NiceHash availability, because obviously that's low-hanging fruit
Right.
for any guy off the street to attack with. But we're trying to frame our parameterization of this in terms of the global availability of ETH compatible hash rate. So basically our scenarios are trying to handle cases where the biggest miner on Ethereum, or even even in collusion with each other, would attack Ethereum Classic. They couldn't do that.
Wow. I mean, that's seriously reassuring. I mean,
that's the hope. Yeah.
Because that's a high bar to go after. I think a lot of people would have been, somewhat satisfied with just being able to stop the nice hash kind of market. But the fact that an ETH mining whale wouldn't be able to do it in collusion with others, that's seriously impressive.
And they will get, if they do try to do something like that, they will and can. They could get blocks. They could get more blocks than a smaller attacker. That's by design, right? Because they can beat that curve for longer. But the difficulty will catch up with them. And the artificial finality curve is ruthless. Yeah.
We just got an interesting question from Greg. I think you might know him, Austin. And he was asking what the cost of this attack that we're simulating now, if we have a rough approximation, what something like that would cost.
So there's a lot of variables, and we were just discussing some of the complexities of this last night. Greg and I, who's asking this question, so basically, in general, you can say roughly the cost of an attack is going to be equal to the hashing power of the network multiplied by the finality threshold for the duration that you want to execute the attack over, multiplied by the duration in seconds, multiplied by the cost of the hashing power. So
you all got your calculators out, I hope.
Well, I did math yesterday, but basically, so if you assume, right now Ethereum Classic has about 1.98 terahashes per second, and on Nice Hash, you can get a terahash an hour worth of terahash second hashing for about $2,000. So if you had a $100,000 transaction that you wanted to reorg out, you can basically kind of assume that transaction is not going to be reorged out after 9,116 seconds, or about 2.53 hours, because beyond that, the cost of executing the attack is going to exceed the price of the transaction that you'd be trying to reorg. Now, of course, there's other variables that feed into this too. So if you're executing a double spend attack and it gets a lot of attention, well, then maybe the price of ETC drops off a bit, and so the
price of Nice Hash goes up a bit.
Right. Yeah. So the price of the hashing power moves up. So your first unit of hashing power is going to be cheaper than your 1,000th unit of hashing power.
Right.
And then, but there's lots of other variables that feed into this. How do you account for the ETC that you've actually mined during that period? So you're going to be able to sell that too, which isn't necessarily going to overcome the cost of what you paid for the hashing power, but it feeds into the equation. There's lots of variables in that equation, but ultimately, you can generally look at the finality curve and the cost of a transaction and figure out. You also need to consider the cost of hash power and the amount of hashing power currently on the network, and given that, you can figure out how long or how costly it would be to execute a reorg over a given period of time. And based on that, you can generally assume that transactions smaller than that are probably not going to get reorged out because it wouldn't be cost effective to do so.
Okay, I hope Greg likes that answer. I think he seems satisfied with it. Julian gave us another one. And now, by the way, I'm choosing questions based on the number of votes. So if there's a question that you want us to look at, and you think we need to address it, please click upvote so we can see it. Can potential clock differences in clients made some accept or decline some branch over the other, and in so increase the probability of orphan blocks?
Can potential clock differences in clients make some accept or decline some branch? Okay, so clock differences in clients is a thing, indeed. Although in practice, they're probably quite small, but across the network, you do expect that that miners will have faster clocks than non-miners.
The other thing I want to point out here real quick is that typically miners, when they're working on a block, they establish the block that they're going to work on, and then they start hashing on it, trying to come up with the nonce.
Oh, look, our attacker is going to win.
Oh, yeah. Okay, so the attackers just moved in. But
how would you see this? Because I only see one column.
Yeah,
what?
they'll come.
So I see the one node column that has the longer chain. Oh, I see it now. Oh, all the other nodes are
jumping up to that level. It's skipping the intermediate steps, and they're jumping straight to that level. But back to this question: the potential clock differences of a few seconds here, a few seconds there, usually, and those are problems that don't really impact MES significantly. Those are things that are present on the existing Ethereum blockchain or Bitcoin blockchain or any other blockchain. They typically tend not to be too significant because, as I said, miners tend to pick their blocks and then start mining on them. So by the time they've actually found a nonce that makes that block valid, the block is already a few seconds old. And then it takes a bit longer to propagate out across the network. So if they are honest mining, it require very significantly different clock times before people are going to start rejecting. And again, this is standard Ethereum stuff. This is not anything specifically to do with MES.
Yeah, and it's to follow that. MES's parameter, which is kind of its domain for this curve, is in seconds, and that value is measured not by the system clock time, but it's measured as the difference between the nodes, the timestamp of the load's local head against the timestamp of the common ancestor for the reorg. So system clock times are not at play. It's just the block time stamping, which builds on Austin's point that system clock times is a stable system in the Ethereum Classic, and proof of work networks. Stable, but variable.
Okay, great. And it looks like Julian understands and appreciates that answer. There's a few, let's see, it's hard to, if the network is attacked only, this is a question we've also seen on GitHub, mentioned from Kevin, which has to do with some clients might not have MES. What would happen to the clients that don't have MES?
Yeah. So MES is working towards the part of the chain that has to do with its growth. So the the general concept is to try to only grow the non-suspicious chain. So in that way, the most important part for network adoption is with the miners. If we have the miners on board with this, the honest chain will be safe to that degree of miner adoption.
Right, and CoreGeth is the majority client.
Yeah.
Yeah, especially among miners.
Especially for miners. So the question then is, okay, so what happens then if there's two scenarios. What happens if only some share of the miners adopt MES? And then the other question is, okay, well, what about for non-miners and viewers of the network, like exchanges or anybody who wants a view of the network? What happens to them if they don't adopt MES? For that second part, if you are running a node as just a view or a read-only node for the network, then if you're not running MES and MES comes into play with the mining nodes and it does impact chain growth in some way, then you will have a view of the network that would be a view of potentially of the attacker's chain. And again, though, that will only be for the duration that the attacker is beating the total difficulty of the honest network. So it's only for that attack time span. Because then without MES, your node will automatically find the chain with the greatest total difficulty. For the scenario where miners, some share of miners adopt MES and some share don't, that can just be considered as causing the network, for the miners that don't adopt MES, assuming that the attacker can beat the total difficulty of the honest chain, which we are assuming here because this is about 51% attacks, and bringing outsized shares of hash power to the network, then those miners will be mining on the attacker's chain. And nodes with MES would reject that chain and continue mining on their chain. So again, it's the same scenario. As long as the attacker continues that, then if the majority of mining nodes don't have MES enabled, then that will grow. And that will become the chain. That will become the canonical chain because the majority of mining nodes didn't have MES enabled and preferred to mine on the attacker's chain. If the majority of mining nodes do have, of mining power, I should say, because it's not about node count, it's about hash rate. If the majority of honest Ethereum Classic Network hash rate does adopt MES, then that chain will eventually prevail.
Right. The attacker might be able to dominate the network for a while. They might be able to bring some people on board mining with them, but so long as they don't have the majority of the honest network, they have to sustain that attack themselves, which gets very expensive.
So it would be fair to say that MES gets stronger the more people adopt it, but at the same time, it doesn't make the network any weaker if it doesn't have, 100% adoption.
Right. 100% adoption is not necessary. Really what we need is a majority of the hashing power. And the other thing that I want to note is, CoreGeth supports it. Besu is going to support it, although probably not quite on the timeline where it's going to activate for CoreGeth, but that's okay, because we've looked at the mining power, and it does not appear to be the case that Besu holds in anything resembling the majority of the hashing power on the network.
Mm-hmm.
So we're nearing the 1 hour mark. Thank you everyone for the fantastic questions. I think we should cover the last group of questions we have. There's two questions that connect to the hashing algorithm discussion. One is, why do we need to change algorithm when MES can increase network security? The other one is, so with MES, it only works reliable on ETH hash and not KCAC 256 or SHA-3. So I'm pretty sure that MES is algorithm agnostic. It could work on ETH hash or KCAC or SHA-3.
That's correct.
Okay, great. And then on the question of why do we need to change algorithm, I think that those are two separate discussions, if I'm also fair, which is, MES helps in a, quick situation where we're in, of protecting the network and helping hash rate go back up, whereas an algorithm change is a much more involved, bigger decision that, MES can help us move towards later on, but I don't believe that they're codependent. Is that fair?
Yeah, they're very independent ideas.
And I guess MES may slightly move the needle on that, in that part of the motivation for changing mining algorithms was to decrease the availability of market-based hashing power like NiceHash. And that becomes less of a concern with MES, but there are other factors that feed into that, which I'm not remotely qualified to talk about. So,
we have another question. So, is it possible to overrun MES by running multiple 51% at the same time?
Yeah. Interesting question. So, so first, worth off the bat saying that a multiple 51% attack, if we say that let's consider a case of two 51% attacks. At large, that is somewhat equivalent to a 66% attack. Because we're going to have the honest hash power. We're going to have one bad guy who matches the honest hash power and another bad guy who matches the honest hash power. So 66% or 2/3 of the network's hash power will be controlled by one or two bad guys. But the most potent form of that attack would be where they're controlled by one entity, right? One human sitting behind the wheel, so that they can work those in coordination. Second off the bat, second base for that is that means being a 66% attack, that means it's twice as expensive as a 51% attack.
Yeah, so they kind of fight each other and help us by having two people attacking the same.
Well, we would assume that if they're one operator who's worth his weight, he wouldn't have them fight each other, or at least he would have them fighting each other if he thought that was going to be his strategy. Now that this scenario is, from the algorithm's perspective, equivalent to mounting a 51% attack twice. Because we're confident that you could mount a 51% attack a whole heck of a lot of times and still be unsuccessful, that I don't think that it's two drops in the bucket instead of one drop in the bucket. Yeah. I hope that answers it.
I mean, I feel that I understand it, which basically is, if that happened, it would just be so much more incrementally harder for those people to attack, because they're attacking each other at the same time. Everybody's trying to get that control. The price, if they were doing NiceHash, would go up because those units would be in demand from both bidders. No, I think that was satisfactorily answered. So there are two more questions, and then we're going to stop taking questions here. Of course, you guys can continue asking questions in Discord. We're all available on Telegram, Twitter, wherever. 100% we want to answer every single question for this, but these are the last two questions we're going to address. From Greg, how do exchanges that off-ramp to fiat or other chains tokens benefit from MESS in terms of how they set policies like number of confirmations?
So again, what MESS does is it increases the cost of running an attack. It doesn't make it impossible, but it increases the overall cost of how much hash power you have to buy in order to be able to execute a successful attack that could potentially undo transactions. And the main thing that exchanges are worried about is somebody makes a deposit, they accept that deposit, trade it for something else, the person withdraws that to another chain, and then that transaction gets undone, and now they don't have the tokens that they're supposed to distribute in exchange for tokens that they already distributed. When I was getting into my cost calculations earlier, you can pretty much assume that given the current parameters of the network's hashing power and the cost of buying hashing power, that $100,000 transaction, for example, will be safe after, say, what was it, 2.5 hours, because beyond that, it's going to cost more than $100,000 to execute an attack to reorg out that transaction. Now, exchanges should still be cautious of the fact that people, there might be multiple transactions that are going to get reorged out at the same time, so they should maybe look at their total exposure instead of looking at individual transactions when they decide whether or not they're going to consider it final. But essentially, there is a nice curve where if exchanges want to pick a fixed number of confirmations, with MESS, the difficulty locks in or the finality multiplier locks in at 31 times at about 7 hours. So that they may want to pick 7 hours as their target. But if they're okay with the idea of having some flexibility in the size of transactions, a $20 transaction is never going to get reorged because you can't execute this kind of attack on
Right.
$20 or on a $20 transaction profitably. A $20 million transaction, you might want to wait a bit longer than that 7 hours. Like a $20 million transaction could be reorged cost effectively up to, 13 or 14 hours.
Yeah, and to put things in perspective, right now some exchanges have confirmation times that are, days at this point. So, the fact that you can lock in the 31x difficulty with 7-hour confirmation times, that's a huge a move in the right direction right now.
And ultimately, I think we can get it pretty safely to where they can conduct these transactions within a single business day.
Yeah. So I think that answers the question. It's a great thing that confirmation times can safely come down at this point once MESS is implemented. There's a great question to segue to that, which is how long does it take to activate this feature? And I do want to point out this is an ECBP, not an ECIP.
Yeah, this is an Ethereum Classic proposed as an Ethereum Classic best practice, which is to say that it's a proposed convention for clients to adopt.
So once it's on the client, once Core Geth and every other client has MESS, how long would it take for someone to activate this?
Yeah, so we have we've had this implemented in some shape or form in Core Geth for I think at least a couple of weeks now, and we are very much nearing the end of our test, of our going through the paces of our tests, both with MESSnet and locally and otherwise. Right now, the spec, optimistically, although still tentatively, is proposing the activation to land on mainnet in a week from today for CoreGeth clients. Our team has been in touch with ETC Labs has been in touch with the miners, and from what we gather, they're on board with this and ready, willing, and eager to adopt this. So that's a rosy picture for us right now. The timeline for that depends on just some of these final stages of review and approval and merging for this for the feature, which I'm hoping to shoot for today or tomorrow, and we'll be on the road.
Excellent. Great answer for that. And now I think there's just the last question. Guys, thank you again for your questions. We won't take any more questions. We'll have to take them on to the Discord. If MESS is implemented to begin with only in CoreGeth, can ECIP 1099, which is the DAG size reduction, can that be performed at that moment and then BESU join later?
ECIP 1099 is a very independent, mutually exclusive idea to what MESS is. And it is a consensus protocol change. So it will require a hard fork, will or would require a hard fork. And it is not expected or anticipated or planned at this, as far as I know, and at this point, for those two to be related in terms of their timeline.
And if you did execute the 1099 change at the same time that we're planning to execute this, BESU nodes that haven't implemented 1099 will be left out in the cold, and they won't even be able to keep up with the chain, let alone mine.
Got it. Yeah. So the DAG size is even though the impact of MESS is large, it's the DAG size is a change that could have more complex ramifications across the network.
That's right, and it's my understanding, although of course I'm not on the team that makes these decisions, but it's my understanding that the changes for BESU are planned to be ordered as 1099 first, and then to implement MESS later or after that. So that that they have the maximum amount of time to be prepared and tested for a hard fork.
Well, I think we covered all of the questions, guys. This was a great presentation, if I might say, because I've learned a lot too, and I work pretty close with you guys as well. A lot was learned today, so I expect we're going to see more questions come. I hope over the within the next week. Isaac, Austin, we can also have a separate, follow-up interview discussion so we can go over some of the implementation and what people need to do. At this point, the timeline is 1 week from today. We will constantly be posting every single update in Discord, on Twitter, in Telegram, in GitHub. If you have any questions, don't hesitate. Ask. It's important that everybody understand this. And thank you for joining us on this broadcast. Austin and Isaac, thank you guys very much for your time.
Absolutely. Thank you.
Okay. Take care, everyone.